So now we are going to go about proving Binet's formula in a different method than the book does using strong induction. As I've mentioned, the strong induction proof is anticlimactic in the sense that it does not tell us where the square root of 5 or the golden ratio is coming from. So instead we are going to prove this using linear algebra. Since the proof is rather computational and involved, I'm going to sketch the ideas and give some of the computations as fact, and I leave that for verification. So let's discuss the theory. How can we use linear algebra to find that the m Fibonacci number is this here? So here's how. So the first thing is that we want to construct a matrix. So we want to construct a 2 by 2 matrix, A, which has the property that if we take A times the column vector f sub n times f sub n plus 1, this is going to output f sub n plus 1 and f sub n plus 2. So how can we find such a matrix? Well, let's go ahead and put a 2 by 2 matrix A, B, C, D. We have our column vector f sub n plus 1. By matrix multiplication, this is A times f sub n plus B times f sub n plus 1, and then C times f sub n plus D times f sub n plus 1. If we want this property to be satisfied, if we want f sub n plus 1 in the top entry, all we need to do is take A to be 0 and B to be 1. And we get what we want. So we have A equals 0, B is equal to 1. And if we want f sub n plus 2, which by definition is equal to f sub n minus 1, f sub n plus 1 plus f sub n, then all we have to do is take C and D to both be equal to 1. And so that gives us the matrix A, which is now 0, 1, 1, 1. Notice that in defining A, the only thing that we use was this fact about how the m Fibonacci number is attained. We haven't used the actual numbers. And so this actually extends even further to giving us methods for finding closed formulas for a given sequence defined recursively. And so this approach that we're doing to find the m Fibonacci number can be used to find the mth term in a sequence where that sequence is defined recursively, similar to how we're defining the Fibonacci numbers. Okay, so let us continue. How are we going to use A for what we want? And here's the way we're going to go about it. So we take A, and we multiply this matrix A by the column vector 0, 1. Then we're going to get back 1, 1. But 1, 1 is F1 and F2. What if we multiply this equation by A again? That will give us A squared, 0, 1, is equal to A of 1, 1, which then gives us 1, 2. And now that is F2, F3. Okay, what if we continue? What if we do A cubed? So now this will be A cubed of 0, 1 is going to be equal to A times 1, 2, which is now going to give us the column vector 2, 3. Or in other words, it's going to give us F3 and then F4, the 4th Fibonacci number. And so on and so forth. And so what we are seeing is that by taking A to the n of 0, 1, when I say A to the n of 0, 1, I mean the matrix multiplication A to the n times the column vector 0, 1. What we are getting back is the m Fibonacci number and then the m plus 1 Fibonacci number. And so what we want to do is find a formula for what A to the n is. Because if we find what A to the n is as a matrix, then we can just take A to the n, multiply that by the column vector 0, 1, and the top entry is equal to the nth Fibonacci number. So how do we find a to the n? Well, from linear algebra we know that finding the nth power of a matrix is made very simple through diagonalization. So the theorem that we want to invoke from linear algebra is the following. So before we state the theorem, let's go ahead and say that we have A is an n by n matrix, and lambda 1, lambda 2, all the way through lambda n are eigenvalues of A. And so what the theorem tells us in this notation is that a matrix is diagonalizable if and only if there is an eigenbasis for the matrix A, and if v1, v2 through vn is an eigenbasis for A. And so recall that when we have an eigenbasis, it's a basis composed of the eigenvectors v sub j. And so in other words, we have, by definition of an eigenvector, that corresponds to an eigenvalue lambda sub j, that we have A times v sub j is equal to lambda sub j, v sub j. And so if we have this, then the diagonalization of A is given in the following way. We have S inverse A times S is equal to B, where B is the diagonal matrix. Moreover, we also know from linear algebra that if we take B to the n, if for any diagonal matrix, this is just going to be raising the terms along the diagonal to the nth power. And actually, because we're working with an n by n, let me switch these exponents to m. And so we have a diagonal matrix where all the terms along the diagonal are raised to the power that we are raising the diagonal matrix. So how does this help us? Because in our case, our matrix A is 0, 1, 1, 1. If we were to find that it's diagonalizable, if A is diagonalizable, then we know that there is going to be an invertible matrix S and a diagonal matrix B. Then there is a diagonal matrix B. And invertible matrix S. Such that A is equal to S times B times S inverse. And so here what we have done is multiply in this equation by S on both sides, so that S times S inverse becomes the identity, and then we have A times S equals SB. Then we multiply again on the right hand side by S inverse, and so that will lead to S times S inverse being the identity, and we have S times B times S inverse equals A. And now, as a consequence, we then get that A to the n, which is equal to SB times S inverse to the n, which is the same as saying SB S inverse, SB S inverse, all the way to SB S inverse, where we're doing this n times. We will have cancellation, because now S inverse and that S will cancel. And so this will cancel off here. And so what we end up getting is that if we look at the matrix multiplication B S inverse SB, that's just going to become B squared. And then the S inverse over here is going to cancel with the one that's on this side, and then that S will cancel with an S inverse to its left. And what we end up getting in the end is that this will ultimately be S times B to the n, S inverse. So our question of finding A to the n times the column vector 0, 1, if A ends up being diagonal, which we will show, then this will result in SB to the n, S inverse, times the column vector 0, 1 gives us back the nth Fibonacci number and the nth plus 1 Fibonacci number. And so that's where we are headed. So we want to diagonalize this matrix which by the theorem means that we have to find first its eigenvalues and then the eigenvectors corresponding to said eigenvalues. So let's go ahead and do that. So we have A is 0, 1, 1, so its characteristic polynomial is going to be the determinant of A minus x times t 2 by 2 identity matrix, which is the determinant of negative x, 1, 1, and then 1 minus x. And so now this will give us negative x times 1 minus x minus 1, which simplifies to x squared minus x minus 1. The eigenvalues of A are the roots of the characteristic polynomial. Then you can verify that if you set via the quadratic formula, if you find the roots of the characteristic polynomial, this will imply that x is equal to 1 plus or minus root 5 over 2. So the eigenvalues of A are lambda 1, 1 plus root 5 over 2, and lambda 2, 1 minus root 5 over 2. So we got our eigenvalues. The next thing we need to do is find the eigenvectors corresponding to these eigenvalues. So to that we need to compute the eigenspace. So we want to look at E sub lambda 1, where E sub lambda 1 is the kernel of A minus lambda 1 times the identity, the 2 by 2 identity matrix. So we're looking at the kernel of the matrix. So now we have lambda 1, negative 1, and then we have 1, 1 minus lambda 1. So we're looking at this kernel. But to find the kernel of a matrix, so by definition, this here is the set of column vectors in R2. And here the R2 notation is as we use it in linear algebra, not in structures where we're using it as ordered pairs, but we're thinking about this as a column vector. This is the those column vectors such that negative lambda 1, 1, 1, 1 minus lambda 1 times x is equal to the 0 vector. So we're looking for those column vectors that when we multiply it to this matrix, we get back the 0 vector. So how do we go about computing that? By computing the row-reduced echelon form of said matrix. So we have to find the row-reduced echelon form of negative lambda 1, 1, 1, 1 minus lambda 1. Now, if you go about computing this, what you're going to find is that this is 1, lambda 2, 0, 0. And so that's what's going to be the row-reduced echelon form for this matrix right here when you run through the argument. So where does that leave us? Well, if we have the matrix in row-reduced echelon form, then the kernel for this is the same as the kernel of this. And so we put it over here, kernel. So these kernels are going to be the same. And so now what we want to do is look at our column vector, 1, lambda 2, 0, 0, times an x1, x2. So this is the column vector that I refer to over here as just x vector. And so this is going to be equal to 0. But this tells us that we have the equation x1 plus lambda 2, x2 is equal to 0. Since we don't have a pivot in the second column of this matrix, that means that x sub 2 is a free variable. So note, x sub 2 is a free variable. And so let's go ahead and take x sub 2 to be t. So in that notation, we will have x1 equals negative lambda 2 times t. And if we take t to be equal to 1, we end up getting x1 equals negative lambda 2. And that gives us a vector that spans the kernel. So now the kernel, and actually a basis vector, thus we have that the column vector, negative lambda 2, 1, since x2 is equal to t, which is 1, is a basis for e sub lambda 1, and we have the negative lambda 2, 1, which I'm going to denote by v1, is an eigenvector for lambda 1. If we do the same argument for the eigenspace corresponding to the second eigenvalue, so 1 minus root 5 over 2, then we end up getting that there's only one column vector in its basis, namely negative lambda 1, 1, and that's a basis for the eigenspace. And so now we have, for lambda 1, we have the associated eigenvalue, negative lambda 2, 1, and the eigenvalue lambda 2 has the associated eigenvector, negative lambda 1, 1. Now we can apply the theorem. We know that A is diagonalizable. And so the theorem tells us that A is equal to SB, S inverse, where S is going to be the 2 by 2 matrix, where we go ahead and put one column to be V1, the second column to be V2. So we have negative lambda 2, 1, and then second column is negative lambda 1, 1, and B is the diagonal matrix, where it's just the eigenvalue. So now we have lambda 1, 0, 0, lambda 2. And now we can finally look at what is A to the n of 0, 1, which we know that it's going to output the n Fibonacci number and the n plus 1 Fibonacci number. So this is going to be equal to SB to the n S inverse, 0, 1. And so still, we have to compute this, but this is a much easier computation because B to the n is simply going to be lambda 1 to the n, 0, 0, lambda 2 to the n. So if we go about computing this, we get the following. And so we get, after doing the computation, that A to the n, 0, 1, is going to give us this column vector. But to find the n Fibonacci number, we know that that's just the first entry in the column vector. And there we have it. We have Binet's formula by doing this matrix multiplication. And we are done. We have computed the n formula, the n Fibonacci number. And in the process, we see that 1 plus root 5 over 2, 1 minus root 5 over 2, they are arising from the eigenvalues of the matrix A. And that is the aspect that we fail to see when we prove it by induction. Induction allows us to show that a pattern that we expect to be true is true, but it doesn't necessarily tell us if that pattern is arising from something deeper. And this is an instance where we can use linear algebra to find the nth term in the Fibonacci number, but more generally, we could do this for sequences that are defined similarly to the Fibonacci sequence.